All right, good morning, everybody, to this happy Friday, where we are continuing our discussion on limits. Lots of little things. The more I think about this, the more there are just little things that I need to see, that I need in order to form a big picture around what limit questions I have to be ready for and understand. And unfortunately, the confusing part comes that we have to break it up over multiple days. We have a weekend in between where the picture isn't quite complete. But hopefully, looking back, it will be better than it might feel in the beginning. It's unfortunate when we have a picture we're trying to paint, but we need time to do it. It's tricky sometimes. So patience, and it'll all work out. I have thought this through. Do not worry. So, what have we done? We have done something. Let's see here. So far, we've looked at infinite limits. That is where I like to start because it emphasizes the behavior, infinite limits as a long-term behavior question. And because we're taking a slightly informal approach to limits, it's very important to understand what they are trying to express in the mathematical language. It's all about behavior, asking the behavior question. Now, for example, limit as x approaches infinity of, let's say, 2x over x to the 5 plus 1. Random example. We've also introduced the form of the limit, which can quite often help me figure out how the pieces interact, or worst case, tell me that there's a little more to it and I need to take another approach. Either way, it has information and I always want to do it. But it is a little hand wavy, right? What I'm doing is look at, okay, how does just 2x behave as x goes to infinity? Okay, infinity. It doesn't tell me how fast or anything really, but it tells me that it is growing as well. X to the 5 plus 1 also growing. Now, that's not a number. The risk, I guess, is when I write something like this, there are people, regardless of my best efforts, there are people that think, oh, infinity over infinity, I cancel them and it's equal to 1. Well, I mean, at some point, I just can't help you anymore because nowhere in your math schooling has anyone said infinity is a number, and it doesn't follow the same rules. It is simply an indication of unbound growth. It doesn't follow the rules. So when I write it like this, it might be a little deceptive. This is just for us on the side, unofficially, to investigate and get a little bit more information as to what this function is all about. Okay, so see it for what it is, and we'll be fine. So this then tells me, oh, infinity over infinity, they're both growing. I can't really conclude anything because it's then a matter of how fast they're growing compared to each other, which means I have to go and look at my function. In this case, it's a rational function. That means I compare the leading terms and its behavior under these x conditions is equivalent to the behavior of the ratio of leading terms. I can cancel one of those x's, leaving 4 at the bottom. More x's in the bottom, constant in the top. I can do the form again. Form of this is a constant 2 for the numerator and something that blows up for the denominator. Well, now this form tells me a whole bunch to the point where I don't have to do anything anymore. If I have a constant at the top, and something that blows up in the bottom, this guy is going to shrink to 0. There is no other way. So see how I can always use the form. Whatever limit I have, the form tells me something. It could be very good news. It could be just news. Either way, I have more information. So it's definitely something I want to keep in mind. So infinite limits, meaning x approaches plus or minus infinity. Not the answer is in infinity. The answer could be whatever it wants to be. I don't care. Okay. But of course, then it's reasonable to say, well, I could ask the behavior question for x approaching a specific number. It doesn't have to be far to the right, far to the left. So let's see. So let's just make an example before we go to the problems. The example I have is y equals 1 over x squared. Now, I'm going to draw this for you. It's not a basic function that we have because it's not a transformation. It's not one of the simple transformations of our rational function, even though this is a rational function. The graph looks like this. And you can plug in some numbers and convince yourself, and it's not overly complicated like that. So we see that apart from the long-term behavior question, there is an interesting thing happening as I get close to 0. This function is undefined at x equal to 0. However, there is predictable behavior as I get close to 0. The function is, I'll make a big is defined, I'll casually say around x equal to 0 on an interval containing x equal to 0. Though at x equal to 0 specifically, we have a little bit of a problem because we can't divide by 0. We don't have a y value. Anything around even 0.00001, I have a y value. I just can't be at 0. I can be as close around 0 as I want. There's a graph everywhere else, which means I can investigate behavior everywhere else as I get closer to 0. So now the question is, as x gets closer, I'll put here brackets, around 0, how does the function y behave? That is the question. I'm just going to give you a minute. I have to just step away from my computer. I'll be right back, like less than a minute. All right, sorry about that, but it gave you time to think about this. Okay, so there is behavior that I can describe with this. So let's say here the answer is y, let's say, grows in size and is positive. So it's not a difficult thing to observe, especially once I have the graph, right? I now simply want to translate all of this into my mathematical language. So we're going to say, well, limit is our mathematical word for behavior. The behavior of my function, and I like to see the detail, though you could call it just y, as x approaches 0. This is now a finite limit because of what x is doing. X is approaching a finite value. Okay. As we see on the graph, unbounded growth, regardless of where I am, right? The closer I get to 0, the more the y value blows up, the higher the graph goes. But it's predictable. So we can write an infinity there. Still, as we mentioned yesterday, limit does not exist. In this case, this is just a simple first example. We're going to see a lot of examples. If I get a number here, that means the y value can be contained within a small range, and that range gets smaller as I get closer to my desired x value. It sort of stabilizes closer towards a specific number. Great, limit exists. But sometimes there's unbounded growth behavior. I can still indicate that, and we've discussed this yesterday. Don't read too much in the equal sign. It is an appropriate symbol to use. That does not mean it exists because of this infinity that I have there. Okay, so the step towards finite limits is not a huge step. I only look at x doing other things, approaching specific numbers perhaps. Not a big deal. Let me just check here. I wanted to do 14, so why not? Okay. While I'm here, I might as well, I don't know if I want to do it right now. I might as well, yeah. Look at the form of this limit. I can always do that. Why not always then do it? Well, I have a constant at the top, 1 in this case, and my denominator, when I look at it in isolation, approaches 0. Again, that's not a calculation. 1 over 0 does not equal infinity. If you say that, I'm going to ding you. I'm going to subtract marks because it shows a lack of understanding, and that's never something I'm going to write. However, the behavior of a fraction with a numerator of 1 and a denominator that shrinks down close to 0, the behavior tends to infinity. It goes to infinity, that function. So we say the behavior is infinity, though that's also a little relaxed. 1 over 0 is not infinity. I will never write that. So you shouldn't either. I say that because I see people do it. And then you feel cheated when I just start subtracting marks, because I can't confirm that you understand our language here if you just abuse it. So you have to be careful how you write things and how you say things. When I ask about the behavior of a function, this limit portion must be in front, always. I see people just scribble some stuff like, okay, like this. Maybe you want to scribble some stuff there. No, then I read that, and that's not right. You can't do that. Okay. But this is a new form where the numerator is constant. I have a denominator that gets smaller and smaller and smaller and smaller. Plug in numbers. 1 over 0.1, 1 over 0.01, 1 over 0.001. The whole thing blows up. So you can convince yourself that this form does give me a lot of information as to what the limit does. Okay, so I want to do problem 2.2, number 14. Let me just resize this. Problem 2.2, number 14. And of course, ask your questions as you think of them. Don't wait for me to pause and check. 2.2, number 14. 14. I zoom in. Zoom. Ah, you can zoom more. There we go. 14. Nice and big. Very similar function. Limit x now goes to 2. X approaches 2. I already forgot the function. 5 over x minus 2 squared. So the first thing I should check, I want to get into the habit, though rarely it's an issue, I should check it. Is this function defined around x equal to 2? It doesn't have to do anything at 2, because as we saw in this example, scroll down, I'm actually never going to be at that x value. I can't be. Yet I can still ask the behavior question. So actually, the behavior question is not concerned with what is happening at that x value. It's concerned with what is the graph, what is the function hinting at, which way is it going as I get closer to that x value. I will never be there. So we therefore only require that the function is defined around the x value, not at the x value. It could be, it could not be. I could not care less, to be honest. That's not a part of the discussion. The discussion is about what does the rest of the function tell me it wants to do as I get closer? How does it behave as I get closer? What actually happens there is irrelevant. So now I can look at the form and it tells me everything. I have a top staying constant at 5. I have a bottom doing what? On its own, x minus 2 shrinks to 0. So squared also. Question in the chat. Would we expand the denominator even though we know the first term is x squared? Would we expand the denominator even though we know the first term is x squared? That, no. I only have that specific, I think that's what you mean. I only have the specific technique of looking at the leading terms when it is an infinite limit. This is not an infinite limit. Different question. This is not a long-term behavior question. Though it's still a behavior question, it's handled completely differently. The finite limits are not handled the same way. Only the infinite limits. In rational functions, it's a comparison of leading terms. Long-term behavior of polynomials are dominated by their leading term. Short-term, no, it's a mess. It could be anything. And this is a finite limit. But I can still look at the numerator and denominator in isolation to help me figure out how these two pieces might interact. And in this case, it actually tells me a lot. Remember, it's not a guarantee that it will. In this case, however, I have a numerator staying constant at 5. I have a denominator shrinking down. It's not 0. It's a direction. It is a behavior. It's shrinking down towards 0. That means the whole thing is going to blow up to infinity. Limit does not exist. It's really, when you look at it, it's just the transformation of this 1 over x squared function, which I don't have in my library, so I don't need to worry about it. But when you look at the comparison, I'm doing this because it is a transformation of our previous example. But sadly, I don't get a number, so it doesn't exist. There is predictable behavior, but the y value isn't contained to a finite number, so we have to say doesn't exist. But I still like to describe the behavior if I can, which we then do. Okay. Yeah, no, ask as you want to ask. We have time. We have tomorrow on this as well. I'm just slowly running through all the different possibilities. So let's now start making a list here. And you can, after the fact, organize this list as you want. I'm just writing it as I think it makes sense progressively. Feel free to write your own notes. That's always a good idea. And organize this in a way that you can see the big picture. Okay. The notes I write here is not maybe organized and laid out perfectly for your liking. So just be aware of that. We have touched on this simplest case in the past when my function is continuous at the x value in question. And in the behavior limit question, that x value is where I'm headed. Then the limit as x approaches that value of my function is simply the y value when I plug in that x value. Example of that, I have an example. Very nice. Limit x goes to 1 of 5x squared minus 4. Polynomials is a very easy example because it's continuous everywhere. It's a one-piece graph. It doesn't have any strange things happening. It's just one nice and smooth line, connected line. No, it doesn't have to be super smooth. It just has to be one piece. So when I look at a behavior question first, this is the first case I'm hoping for. Is it as simple as just plugging in the x value? Because if it is, then there is no need for a behavior question to be even asked. You're trying to trick me. I can just plug it in. If I get a y value for this familiar looking function, I'm good to go. It's 1. Limit exists. They are trying to trick me. And if I were to graph it, not that I know exactly, oh, this is just transformation, right? Of a parabola stretched, shift down. So over here, at 1, that's a terrible example. It's much narrower than this, isn't it? Let's say 1 is over here. There's my point. As I travel along the graph, what is the behavior suggesting happens to the y value? It's going to the y value. That exists, so there's no issue. What do you mean when you say it is continuous? You have not watched yesterday's video. We did this yesterday. It's defined everywhere. I can draw the graph with one motion without lifting my pen. It's one piece. It doesn't have like this. Now, I know I'm doing it informally for a reason, because when we define these things formally, then it distracts us from our goal here. Look at the graph. If I have to draw it left to right, I'm going to draw this, lift my pen, then draw it again. I make a jump. It's not continuous. So the basic intuitive concept of continuity is as simple as that. Yes, mathematically, things always get more technical. No, I don't need it for this course. So why scratch the surface? Do I lift my pen when I graph it? Do I make a jump? Then it's not continuous. Polynomials, it's always just one graph. It doesn't have any features like that. No jumps, nothing. Continuous. Whatever x value I'm interested in, there's a point for it. There's a y value. There's no issue at all. And I like to keep it as simple as I can to focus on the important things. But yes, if you know a little more and you sit there thinking, oh no, continuity is way more complicated. Yes, it is. We don't need it. We're not going to see the complicated side of it. We're doing Math 108. Okay. So I try and keep things as simple as possible. Limits, in truth, they are horrible little things if you really peek behind the curtain, but we don't need to. We get the job done with this approach, and it's more than sufficient. There's not going to be any question that you can't handle in this way. I will make sure of that. So we always hope for the simplest case, right? We have literally nothing to do. Asking for the behavior when the function is continuous at that x value of interest is the same as just asking for the y value. The behavior is an unnecessary layer when the function is so simple. Now, I will say, while I'm here, for example, if I ask for the limit as x approaches 1 for this function, note that there is no issue there. I am containing myself around a very small window around the x value in question. I don't care what happens anywhere else. Is it continuous on that little window? Yes, it is. 1 over 1 squared. 1 exists. Move on with your life. So I'm only focusing on the window where the x value wants me to focus. Other features of the graph could be in other places. It's not relevant. And I can make my window as small as I want, just focusing right there. What is happening there? I don't care about other jumps happening way off. I'm not interested in that. So it depends on the question. It depends on the X value that I am going to. I only worry about that one. Okay, simplest case. Great, if I get it. But chances are I'm not going to. Though it could happen, I do want to start by checking that first. Now the question is, what else can happen? Okay, so here is, I don't know if I can really order these. Let's just look at an example of something else that could happen. And here, definitely ask if you are not sure, because I might not say things at the time you want. I might not say things in the way you want. I can't see your expression if it's confusion or you're good. So you have to let me know. Let's look at this function. Sure, rational function. Great. X goes to 2. I try the form. Absolutely, I would. Though, look at other textbooks. That's not what they tell you to do. I will always do it because it is always informative. However, when I look at this, I get the numerator goes to 0. The denominator on its own goes to 0. Well, that is not necessarily very informative. 0 over 0 is not 1. If you do that, or if you want to do that, then there is a severe lack of understanding about how numbers and fractions work. It indicates behavior, and that's the question. So now, just like the infinity over infinity case, it's a matter of how fast these two are shrinking relative to each other. Do they balance each other out? Does one shrink faster than the other and dominate the fraction? I don't know. So the exact same situation is happening here, but now for shrinking down to 0 instead of blowing up. So I can't say anything from 0 over 0. But it does tell me. So this, we'll see more examples of this, but this is my other indeterminate form. That's an I. Oh, wow, my writing is horrible. Indeterminate E form. In that it's not clear what the behavior, what the limit answer is. And we'll see soon enough, it can actually be literally anything can happen with 0 over 0. It doesn't exactly determine the answer. But all that means is I have to be a little bit more careful. Look at, just like for infinity over infinity, look at the function I have to work with here. Oh, it's a rational function. But it's not an infinite limit, so how I handle it is different. In this case, I'm going to try and factor this guy. See if that clarifies things, because I see the top is a difference of 2 squares. So I can factor that as x plus 2, x minus 2. I understand as I go, yesterday as well, perhaps you find that I'm speaking very quickly. And it's because there are a lot of little variations I need to get through. You have the video, watch it again. Actually, you can probably adjust the speed in YouTube as well. Slow it down, do whatever you need to do. Okay, you don't have to get everything in real time all the time. Okay, there's just, if I don't cover all the little variations, then you're missing out. I'd rather have this be complete, since there will be a record afterwards. You can repeatedly watch. Okay, but still feel free to interrupt during the session as well. Okay, so now what is this telling me here? This function, I can see a little bit more clearly that the x minus 2 piece, I call it a piece, it's a factor, I know. The x minus 2 factor appears at the top as well. Now I cannot say, let's say here, note, x squared, the function x in its original form, is not equal to x plus 2 when I cancel these two, right? Which I want to do. That is not true. They're not the same. because the left one is not defined at x equal to 0. The right one is. They're not the same function. However, that's not my question. My question is on behavior. So my question is, how do these behave when I'm not at x equal to 2? Well, they're going to behave exactly the same. And the only difference between these two, if I were to graph them, let's do this one over here. And let's do this one over here. There is a very subtle technical difference only between these two. This one, of course, is a straight line, x plus 2, like that. This one actually is almost identical, except it has a little hole that it jumps over when x is 2. It's not defined at 2. But it's not defined in a very different way compared to this 1 over x squared. Very different. And that comes out whenever, oh, I can't see everything. Whoopsie. Whenever I have this cancellation effect, what is really happening is I have this little hole that it jumps over. Little hole. It is a discontinuity. It is a jump in the graph. There's bad things happening there. But when you look at it overall, it's very localized. It's not as big a deal as this guy was, where the y values blew up. When I ask for the limit, I'm asking for the behavior only. Which means I'm asking for, forget what happens at 2. You have blinders on. You can't see it. It's dark there. You can't see it. As I travel, I've lost my writing ability. Nothing is happening. Why can't I write anything? Oh, I was white, that's why. As I'm traveling along the graph, by getting closer and closer in the x value, what is the y value? What is the graph suggesting happens? Am I going to a specific y value? Am I stabilizing? Yes, I'm going to this y value right there. That's what the graph is suggesting. The closer I get to 2, the closer I get to that little hole. I'm never going to be there. I'm looking at the behavior. It's a completely different question, right? Oh, well, okay, not completely different, very similar, but not the same. So by having limit in front, I'm asking the behavior of this function, well, it's the same function, I can now say is the same as the behavior of the function I get when I cancel the two pieces, because I'm not at x equal to 2. I'm not actually going to plug in a 0. They behave the same everywhere else. And all I really need is a window around 2. Do they behave the same around but not at 2? Yes, they do. The only reason these two functions aren't equal is because of what happens at x equal to 2. And when I look at behavior, I'm not at x equal to 2. Therefore, their behavior is the same. But now I've reduced this and made it much simpler, where I can look at a function that has the same behavior, but it's much easier. Polynomial. Super easy. Plug in a 2, I get a 4. That means this y value that it wants to head towards is a 4. It'll never get there. The behavior question never puts me at the x value. It's just getting closer and closer to the x value and then asking, what is the y value? What is the graph suggesting is going to happen? I can't see what happens there. It's suggesting I'm going to 4. I'm happy. Everything's good. So in these cases where there's sort of a technical problem at the x value, the behavior question becomes more relevant, showing that there's no major issue I just can't be at 2. Everything else, stable behavior, predictable, limit exists, we're all good. It was more of a technicality because I couldn't divide by 2, right? Okay. There's a very big difference between being at x equal to 2 and coming closer to x equal to 2. And the behavior question then sort of takes over. So that's one thing. When I can simplify this, I can factor and see, oh, common factors cancel. For our purposes, that's when this little hole at x equal to 2 happens. That is not really fundamental to the graph, to the function. It's more of just a little technicality, forcing me to ask about behavior instead of y value. Okay. But it's not as bad as you might think, because right away the form 0 over 0 told me to go look at the function and see what I can do. And in this case, if it's a rational function, factoring is what I'm going to do, to try and see what kind of problem is this bottom x minus 2 really presenting. It's not really a big problem. And actually, these two, numerator and denominator, are shrinking down to 0 in a 4-to-1 ratio kind of way. And 0 over 0 didn't tell me that at all. I need to then go look at the function to see, how does this function behave? What does this function require? Can I simplify it? Can I clean it up? Can I look at the behavior equivalent, but of a simpler function? Okay. Just a matter of examples. Let's get to some examples here. Okay, so I want to explore this 0 over 0 case more. Now, unfortunately, hindsight is 20/20. I don't have these examples in the problem book. I'll just make them up to illustrate how 0 over 0 is an indeterminate form and can result in any answer. Okay, so let's look at some examples. I don't know if we can do all of them. I actually don't want to, because we still have tomorrow for finite limits, but we'll get as far as we get. There is no tomorrow, I know, Monday. Let's look at 5 examples that should cover all the different forms, whether we get to it today or not in its entirety. Doesn't matter. The first 3 are just my own examples, because I found they're not a nice representative one isn't really in the problem book for this finite limit section. So I have this one. And it's really just going to be a matter of shuffling these things around, you'll see. So the first thing I do is look at the form. That's my choice. You don't have to. And no books will tell you to do that, but it's so convenient. How could I not when I know it works? Nothing else is going to be as fast as this. Still reliable. Now I look, what does the numerator do? It is going to 0. What does the denominator do? It's also going to 0. Okay. It's not the answer I was hoping for, or the form I was hoping for, but at least it tells me, okay, now go and look at this function and see if I can clean it up and look at a behavior of a simpler function that's equivalent. Okay, well, for rational functions, it's really about trying to factor this and see what I can do. So I factor it, and I see if I can do any cleanup here. Yeah, the x minus 2's cancel, and I can cancel them, still have an equal sign because I'm saying the behavior is equal, not the functions. If you don't have this limit in front and you write an equal, that's wrong, because they're not the same function. The behavior of the original is the same as the behavior of this simpler rational function. It's simpler, so let's check the form of this guy. I have a new function, in the limit question. So let's see if the form is the same or not. Numerator goes to, just to see if you're awake, the numerator approaches what as x approaches 2? No one's awake. I know. I knew this was going to happen. Hopefully you didn't fall and bang your head on the desk when you fell asleep. At least put a pillow nearby. 4. It is not 0 over 0. Numerator goes to 4. Denominator goes to 0. It's a new function. The form could change, which is why I do it again. It's 4 over 0. Now that is a much more telling form. It says the numerator stays constant. Well, it's not constant. It's going to a constant 4, where at the same time, the denominator shrinks to 0. How does the whole thing, the whole fraction, behave? The size is going to do what of the whole thing? When I have a top that is constant to a non-zero number, the bottom shrinks down to 0. Plug in some numbers. 4 over, I know it's not exactly 4, but it's pretty much 4. 4 over 0.1. 4 over 0.01. 4 over 0.001. What happens to the whole thing? We've done this before. Come on. It was up here somewhere. It's the same as this guy. Yeah, same as this guy. It blows up. It gets bigger. Now, sometimes I will say it depends on other things, that this could be a positive or negative infinity. I don't want to necessarily commit right now. The point is the size blows up. I don't want to get caught up. Sometimes it's not obvious. Yes, the size blows up, but is it always positive, always negative? I don't know, but I do know the limit doesn't exist. I'll tell you why in a second. Limit does not exist. Because if I look at this 4 is always going to be positive, right? This 4 is always going to be positive here. But as I am interested in the x equal 2 position, I'm coming towards 2 from either side. I always have a window around 2. So if I'm on the right, then I have a bigger number minus 2 being positive. The whole thing is positive. But if I'm on the other side of 2, then I still get a number really close to 0, but it's always negative. A smaller number minus 2. So depending on which side I come at it, I could have negative or positive numbers. And I don't want to make a big deal of this now when it's going to come up later in a way I can handle much more easily. So if you just put an infinity there, doesn't really matter which one. But if I'm not sure, put a plus or minus. It's all good. It's all good. We don't have all the tools ready to really easily pick out which one. Later on, it's going to become quite straightforward to know which one it is. I don't want to get distracted with that when it sort of takes away from our focus right now. Later on, it's going to be very straightforward to do. And then I might want to know, because I want to graph it. I want to know, does it go up? Does it go down as I get close here? I want to know which one. Yes, okay, sure. Then we have to really figure it out. Right now, I just want to know about the size. Okay, the size gets bigger. Okay, so I can have a 0 over 0 form originally resulting in an infinity and a limit that doesn't exist. All right, it's good to know. Let's see something else. So on a test, would we put plus and minus infinity? For this kind of question, I'm going to accept any sort of infinity here. I don't really care. It's a question of general size behavior, to be honest. Later on, when we want to graph this function, and one of the questions will be this question, what happens at 2, then I need to know because I want the graph to be correct. That's a different question. So any infinity you put there, it has to be an infinity though. Because I understand that our tools aren't our toolbox isn't complete. We can't easily find that infinity every time, so don't worry about it. That's not the goal here, to be honest. The goal is what happens to the size of the y value. Let's look at a very similar one. 2. I'm going to flip them around. It's not very original, I know, I apologize, but it gets the job done. First thing I do, I look at the form. That's literally the first thing I do. And I see, oh, the top 0 goes to 0. The bottom wants to go to 0 as well. Indeterminate form, don't know exactly what the answer is going to be right away, which means I go back to my function, look, what kind of function do I have? Oh, I have a rational function. Let's try and factor this and see if things cancel and good things happen. I have, of course, the 2x minus 2's at the top. I have the difference of squares at the bottom. So now, because I'm only asking for behavior, I can say the behavior of the original is the same as the behavior of the simplified version, even though the function itself is not the same. That almost looks like a 3. I'm talking about behavior, and the behavior is the same. It's a new limit, essentially, so I can look to see if the form has changed. Top one goes to 0, bottom one goes to 4. Wow, that is very informative. I now have a denominator that stays constant or approaches stability at a non-zero number. The numerator, in the meantime, shrinks down to something super small. What happens to the whole fraction? That's where you say stuff. And if you don't know, totally fine. Plug in some numbers. 0.01 over 4. 0.001 over 4. 0.0001 over 4. It's going to shrink down to 0. Does this limit exist? Yes or no? Because you'd be surprised. Getting an answer of 0 is maybe something people can do, but they don't associate 0 with a limit existing. That's a number. 0 is a number. Don't discriminate against 0. It's a number. Yes, it's very special. It's just a number. Limit exists. So having a 0,0 form originally, being able to cancel out that denominator problem, making the denominator 0, means I have this whole issue again, which is a minor technicality, really. But I don't necessarily know that because I don't want to graph this. I don't know what the graph looks like. I gave you the graph. No, not there. I gave you the graph there. In general, I don't know what this graph looks like. Behind the scenes, when I have a 0 over 0 form that I can sort of get rid of, it shows that at the y value of 0, there's just a little hole there. Nothing major happened. Nothing to be concerned with. So now, actually, I'm going to give you the next example. Whoopsie. Do I have space? I do have space. I'm going to give you the next example because we're out of time, but I want you to think about it. Because only by you thinking about it can anything really happen. Any development, an experience. And my writing is super small. Let me just check if this is what I want it to be. Yes, okay. So that's my next one. Now, you go about it the same way. We still have some problems some examples to look at before we are ready for problem 2.2. So maybe we'll go and review other stuff over the weekend. Don't worry about the finite limits yet. But what have we seen here? What's the takeaway? 0 over 0 is informative, but not ideal. in that I could have a 0 over 0 form originally. It results in an infinity as the answer. Limit doesn't exist. I can have a 0 over 0 form originally, results in a 0 answer. Limit exists. Look at what the form is here. We'll do this on Monday, of course. Look at what the form is. Do the same thing. See what you get. And when you zoom out and look at the big picture, it just tries to emphasize that 0 over 0 is, I don't want to say it's bad news, but it's caution. Be aware that anything can happen. And I just have some examples there to help convince you that, yeah, okay, 0 over 0 absolutely means nothing. But it still tells me something. It still tells me, go and look at the function. We don't know what's going to happen. Just be careful. Whereas other forms, and we'll emphasize that as well, where only one of the two is a 0, maybe only the bottom, maybe only the top, those are so informative that I can pretty much just write the answer to a large degree. But regardless, the form of the limit gives me information. It tells me how to proceed, whether I should be more careful, whether I'm good to go and just write the answer. Regardless, it gives me so much information I cannot live without it. And I don't know why this isn't the standard practice, because it's a little informal, right? It's not an official thing, the form of the limit. It's just for us to figure out what this function is all about. And I think because of that hand-wavy nature, people are a little hesitant to put it in textbooks because it's not precise, it's not formal, though you could easily do it like that, but whatever. But I'm not going to take that away from you. This is how we do it. It is the most efficient way, in my opinion, for our level of limits. So try this example. Let me show you again. Exactly like the previous two, follow a similar approach. See what you get. And then if you want to do something over the weekend, maybe check if you have any sort of review things you need to catch up on. And then we'll continue this. There are more examples we should do on Monday. And then we have one more section and limits are done. So quick. Are there any thoughts on this before we wrap things up for today?
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.